Okay, let's start. So first of all, so I hope you're working on the ethics essay now, and what you will then do is submit it tomorrow, and then we will redistribute the essay, so you will get the essay of the other groups in the same block that you are, and then you will present them, and you will discuss them on Thursday or Friday when you meet with the TA. So remember to do a good job. There you can get 2 credits here, 1 or 2 credits for the essay, so that will be added on top of your points, so it can influence your grade as well. Yeah, so we were talking about real-time systems last week, real-time operating systems, and we ended with this view of a system here. So you have physical memory in the processor, and then you can have different processes, and each process will have its own view of the physical memory. So this is called virtual memory here. So, and you can't communicate between 2 processes, because there is, if you share a variable, you can't access a variable from one process to another process. They are separated from each other. And of course, a good reason for doing this is that you would like your system to be safe, in the sense that one process should not be able to listen to what some other process is doing, because then that could have safety problems, of course. And you will really like to separate processes from each other. So, but in some situations, if you're in a program, you have one task to solve, but you really would like to use, for example, multiple cores in your processors. You have multiple computational units, multiple processors, sort of, and you don't really want to separate the different tasks from each other. So then you can use something called threads. So threads could execute on different processors, but they share the same view of the memory. So if you create a variable in one thread, it can be you can access the same variable or memory from another thread. So that you can use to communicate between different threads. But each thread will have its own stack. So for example, variables that are created on the stack will not be accessible for another thread. So it's only global variables that can be shared. And each thread will also have its own program counter, so they will have their own point of execution, so to speak. And then it's the task of the scheduler in the operating system to decide among all the different threads and processes that we have and that would like to execute, which one should be able to execute at a certain point in time on the physical processors that we have. So it used to be only one processor, but these days, we can have 2 or 4 or 8 different processors, physical processes. Yeah. So we will talk about a microkernel. So a microkernel, in this case, is a very tiny operating system. And typically they do, and these microkernels are used to implement real-time operating systems. So a very important task of these microkernels is the scheduling of processes. So with a microkernel, you will have services for starting up new processes or threads. You can also, for example, have different form of timers. So if we are implementing a control task, we would like it to execute periodically. right? So then inside the operating system there will be built-in support for having the function executed periodically, or for having the thread executed periodically. Something that we will also see today is that when you start to have multiple threads executing in parallel and they are accessing shared resources, so it might be variables or it can be hardware that are shared between different threads, then you can run into strange problems, something called race conditions, and to deal with that we will implement some form of synchronization. So we will, and that could be, for example, mutual exclusion regions. So for example, to say that two different threads, they are not allowed to work on the same variables at the same time. So first one thread should do its work, and then the other thread can continue and do that. So that's a form of synchronization. Another form of synchronization could be that some task should not, is listening for some other task to complete, for example. So it's done should task when all the other tasks have terminated. And to do that, we will introduce semaphores. So that's something we will do later this week. And typically in a microkernel, you also have support for inputs and outputs. So, for example, talking to a AD converter, or communicating on a network, or having a screen connected, something like that. So, and in a general operating system, you have many more aspects that we will not discuss today. So we will talk a little bit about the memory management, but not about file system or networking or security. So with that, we switch over to, or dive into a process here. So what is a process? Yeah, so a process can be, as we said before, something that has its own view of the memory, but it can also be, we can also think about the thread as a process. And basically, or from a high-level perspective at least, we can think about the process having three different states: ready, running, and blocked. So when you have started up a thread, so now we can think about the thread initially as a program, right? So when it starts up, it starts in the ready state. And then when the scheduler decides that, okay, now it's your turn to use the processor, it will switch to the running state. So if we have one processor in our system, then only one process can be in the running state at the same time, or at the time. And then it will execute for some time. So let's think about a control task. So it will read the sensors, it will run the control algorithm, it will output new control signals. So when it's done, it will go and it will wait until the next period starts, right? So typically what it will do is then to wait for some timer to expire. So it will then go into the blocked state. So when it's in the blocked state, it doesn't really want to run. It's just waiting for something to happen. And it will wait for the timer circuit to say, okay, now enough time has passed, and then it will go back to the ready state. And then it can be scheduled again. It's important to note that it's only the scheduler that can move a task from the ready to running state. So you can't immediately go from blocked to running. You always go back to the ready. So then the scheduler will keep a queue of processes that are ready to execute, and each process will have a priority. And in a real-time operating system, the scheduler will always pick the process with the highest priority to execute among those that are in the ready queue. So we talked about this transition, we talked about that transition and that one, but there is also one other transition here. And this is the preempt transition. So at some point in time, the scheduler can say that although this process was running, now there is some other process that maybe was waiting for some timer to expire, and then it was moved into the ready state. And at this point, now there is a process with higher priority that might be ready to execute, right? So in a real-time operating system, what the scheduler will do then, if it finds out that there will be a new process with higher priority that would like to execute, that has higher priority than the process that is currently running, then it will preempt, meaning that it will basically throw out the currently running process from the processor, from the hardware, and let the higher priority process to execute on the processor. Yeah, so this whole idea of being able to interrupt some process from running and letting some other process running, that's called the preemption process. There is also something called yield. So for example, a process can voluntarily also give up the right to execute. So then that's another reason why you go from running to ready. So it can give up without really being done with its work, just to give some other process the chance to run. But this is the normal reason why you go from running to ready. Yeah, so we talked about this. So a process can be suspended in two ways. So involuntarily by the real-time operating system kernel, and the reason is that there is a higher priority process that is ready to execute. And it has higher priority than the currently running process. And then it can choose to suspend itself. And if we go back here, so a good thing when a process or a thread is in the blocked state, then it's not consuming any cycles, CPU cycles. So of course, and this is important because think about now if you have some system that is running on battery, for example, and it only has to do compute new control signals very seldom. So then it means that if there are no process that wants to execute, then the processor can go into a low energy mode and not do anything at all until some interrupt occurs, and then some of the processes would like to execute again, and then it will step up. So the opposite would of course be that you had that you tried to do a busy wait loop. So you wanted some timer to expire, so then you were listening to some timing circuit, and then you checked all the time, am I done now? Am I done now? Am I done now? And then you will then do a lot of unnecessary work. But if you can leave this responsibility to the real-time operating system instead, by just saying that, okay, wake me up when this timer has expired, then you will use the resources very efficiently. So this is really the preferred way to do that. And the scheduler, it will basically keep two different queues, the ready queue and the blocked queue. And the ready queue is a set of processes that can be run if given access to the CPU. So it's all processes that would like to execute. And the blocked queue are all those processes that are waiting for some particular I/O device to become ready or on some event. For example, a timer to expire. So one way to view this is to see it like this. So you have the processor here. And then you have a queue here with all the processes that are ready to execute. And the scheduler will, and this ready queue will be sorted in priority order. So the highest priority will be the first in queue. And the lowest will be the last in queue. And then at every point in time, the scheduler will just look at what is the first process in the queue and let that execute. Until, and it will execute until some other process becomes ready, or that the currently running process for some reason will be either done with its, or will suspend itself, or it will wait, it will block, waiting for something to happen. And then, as we mentioned, when the processes goes from blocked back to the ready queue. And new processes are always put into the ready queue. So, next we'll talk about something called the context switch. And the context switch occurs when the scheduler decides to throw out one process and throw in another process on the processor. So what it has to do then is basically to save the state of the old process and then load the saved state for the new process. And what do we mean by the state here? So what is it that we need to save? So in the processor, we only have one program counter. We only have one set of registers. And basically what we have to do then is to, when we do a context switch, we have to remember for each thread, the thread that we will throw out. So we need to remember where the process counter were, meaning that the address for the current instruction in the program. And we also need to save the value of all the registers that we have in the processor. So we store them in the main memory instead. And then we bring in the state of the new process. So we read the registers that were the value of the registers for the last time that process was executing, and we set the program counter to the right address where for the instruction where we were last executing. And this whole process is called the context switch. And of course, this is some overhead. So the context switch, when we do the context switch, we don't really do any useful work. And usually, you can say that the context switch, this is something that is done very efficiently. So in most cases, the time to do the context switch is negligible compared to all other time that we have. But of course, there are some instructions that need to be executed, so it will take some time. But this is microseconds or even less than that. It could be in nanoseconds as well to do this. Yes?
Is context switch the same as preemption?
So a context switch takes place when you do a preemption. But the context place also, or a context switch also takes place when you do, for example, when the process will give up its execution by doing a yield, for example. So so the context switch is just this process when you throw in one process and throw out the old process. Coming back to the scheduler. So this is the part of the kernel which is responsible for deciding when or which process to execute at any particular time. And in a modern real-time operating system, it can preempt other processes, for example, or so it can suspend them from running and then resume them at some later point. And you can have different policies for doing this. We will talk about two. Rate monotonic, or fixed priority, you can say, and earliest deadline first, which is where basically you change the priority while the program is executing. So we will do that later in the course and see what consequences these different scheduling policies have. So the scheduling decisions, so it might take place when a switch from a running to a blocked state, or from a running to ready, or from a block to a ready state, or when a process terminates. So basically all the transitions we have in the state graph of the processes. So that was a sort of introduction to what's going on inside the real-time operating system and the different responsibilities that we have. And what we will talk about is mainly this scheduler, because it's quite interesting. And it has effect also, or it will also affect control behavior. We have multiple control tasks that are sharing a processor. So we started last week to talk about hard and firm real-time, hard or firm real-time system. And in what we saw was that in most control systems we have firm real-time systems, meaning that we would like to meet the deadline, but usually it's not a disaster if we miss one or two deadlines, but we don't want to miss too many. And a problem is that we have, typically we throw several different control tasks on the same processor, but it can also be other tasks, so it's not necessarily only control tasks. It can be interacting with the user or logging, etc. And they communicate with sensors and actuators, and there might be a network involved here as well. So we will then look into real-time operating system. So this is what we will actually do today. So we will look at one example of a real-time operating system, namely FreeRTOS. And FreeRTOS is the real-time operating system that you have on your Crazyflie. So it's open source. You can read all the source code, can do changes to it if you like. You don't have to do that in this course, but still it's small enough so you can actually go. I mean, if you're interested, you can actually go and read everything that's going on here. So and what you do in this FreeRTOS, you have the creation of tasks. You can have different task dates, and you can delay tasks to implement, for example, periodically executing tasks. And then what we will look into is the shared memory programs. Which is the problem I started talking about when you can have race conditions, for example, when you have multiple threads that are updating a shared state, so for example, a shared variable. So this is how a task looks like. So it's basically a function So you see here, so it's a function of type void, so it doesn't return anything. And it will have a couple of or it will have a pointer to some parameters. So you can actually send in parameters to a task. And it can have variables declared inside the function. So the variables here will now be created on the stack for this specific thread. And then typically you will have a loop like this. So this is an infinite loop, so it will just continue to execute. And in real time or embedded systems, you typically continue to execute until you turn off the power. Yeah, and if you for some reason would like to stop executing, then you should call this vtask delete, otherwise the system might have a strange behavior. But this is not something that you would need to look into. But I think that maybe I will give you a full example here. No. Okay, so this is a small program. It's actually a solution for one of the exam questions last year. So we can look at this program. So as usual, we have a main method here. So doesn't take any, just the void type here because we don't care about the arguments here. It will have we initialize some variable, counter, and in this case, counter is a global variable, so it will be a shared resource. So it's an integer. There's also a keyword before here called volatile. That basically means that this is a variable that you should not try to do any optimization on. And yeah, I will explain why later. So for the moment we can forget about, here we create two binary semaphores, but we can just see that we create 1, 2, 3 different tasks. Okay, so here, increase counter task. To look at that, let's see, go up here. So we see that increase counter task is the name of a function. So we create this task by specifying a function name here. And this is the point where this thread should start to execute. And then we give it some name here. This is basically just for debugging purposes. We also specify some stack size. We have some other argument here that is not I think this is the parameter. We would like to send in that. So we don't send in any parameters in this case. And here we specify the priority. So 0 is the lowest priority, and then 1, 2, and the higher number you send in, the higher priority this task will have. And then we send in some data structure here as well. So see here we send in the task handle. So the task handle is a variable, so it's a global variable that we declared up here. And now by putting the ampersand before, what do we send in? Yeah, the address to that variable, so the pointer. Yeah, so we have
It's at 2
Sorry?
2 o'clock. Is the break.
It's 2 o'clock. Yeah, I'm so afraid I will forget about the time again. Yeah, so we have 15 more minutes to look at this. Okay, so this was the creation of one task. And then we see that we create another task here called decrease counter task. So it's here. Right, so it's another function. And it does something. We don't really care about what it's doing at the moment. And then it's creating a third task, print final counter task, which is here. And what this task will do, we'll come back to that, but you see here it uses some semaphore here. So it will basically wait for the other two tasks to finish their job, and then it will, in this case, print out some value here. And one thing we can notice here is that they all have the same priority. So if you remember, I talked about that real-time operating system will always look at the priority of all the processes in its ready queue and pick the one that is with the highest priority to execute. So what we see from this example is that they don't necessarily have to be unique. You can have several different processes with the same priority. And typically what an operating system will do in this case is that it will divide the time into different slots. So it will execute one process for a certain time, then it will switch over, execute the next process for some time, and then go on to the third and then back. So it will try to be fair among all the processes with the same priority. And here, the last thing we do is that we actually start the scheduler. So now when you do this, all the different threads can start to execute. So this is an example how you can do this, but if we have left out some important parts here, we could, for example, this will return a number here, so if this was successful or not. So it might be that you run out of memory, for example, so it could be that you're not successful in creating a task. So then you should listen to that and figure out how to deal with it. But assuming that, so this is, we try to keep things condensed here. We have left that part out, just to give you an idea of how to write such a program. Okay, so what will happen now, you have the same priority for all the different threads, so they would like to start to execute. You will have initially 3 different threads in the same, in the ready queue, right? And what we got here was threads. So remember now, because we had this global variable counter, so now we could refer to this global variable from this function that was connected to task number 1, this that was connected to task number 2, and it was also read here in the third task. Right? So they are sharing memory now. We can refer to them. So it's not processes in the strict sense that they are separated. Instead, it's threads that we have here. Okay. If we look what we're doing here, you can see here. So we have increase counter task. So what is it doing? So it creates some variable I here. So that will, and then it will iterate from I equal to 0 to I equal to 10 million here. And every time it will increase the counter by 1. Right? So when this task is done, the counter should be 10 million. Okay? And if we do the same thing here, almost, we iterate, we have another I here. So remember now that this first I is on the stack for thread number 1. This is now on the stack for thread number 2. So they are completely different. But the counter is the same. And what this task will do is to decrease the value by 1 10 million times. Okay, so we have one task that will increase the counter 10 million times, and another that will decrease the counter 10 million times. And then we have a third task here that will wait for both of these to finish, and then it will print out the final value. So what do we expect the final value to be? 0, right? Turns out that if we run this program, it might print something else. And that's the race condition that we will talk about, and we will discuss how to deal with this. But that's something we will discuss mainly in the next lecture. Yeah, so at least I hope you got some idea about how to write to set up a multi-threaded program here. Yeah, so please interrupt me with questions. I'm sure there are. You might have any. Sorry, yeah?
The input arguments to the methods.
Yeah.
Why are their type void?
Yeah, okay, yeah. So you have why this is the void type. Yeah, because it's basically stated that the function that you send into the to create task function has to have this signature. So and the problem is that you don't know beforehand what type of data that you will send in. So with void, you basically say that we can send in any type of data. Of course, in a specific situation, you might send in a string or an integer or something like that. And then what you need to do is to explicitly cast that type. So I have some examples on that later. But I mean, the short answer is that these functions that we start up here, they have to all look the same. It's only the name that might be different. Of course, and then it's just this to wrap your head around how you start to have multiple points of execution in your program. So you will have, so when you have started up all 3 tasks and the scheduler is started, so then you will have one thread that will be at some point in this function, and some other thread that will be at some other point in this, and the third thread will be somewhere here executing. Right? So remember now they will have 3 different program counters. So the program counter will be the address of the current execution for each task. But only one of them will be executing at a time if you have one physical processor. Okay, so this is the state machine again. So remember, these were the 3 states that we saw before. But in FreeRTOS, you also have a 4th state here. So for example, a task can suspend itself for some time. So basically say, okay, for some time I don't want to execute it at all, and then some other thread can start that that other thread again at some later point in time. So yeah, we will come back to this state machine and discuss it in more detail. Yeah, so this was what it looked like to create a task, and we had the first argument here was the pointer to the task function, and then the second was the task name, so used for debugging. We also need to set the stack depth for each individual task. Remember, each task had its own stack, and the stack is at a certain point in memory where you can, for example, if you put on variables that are, for example, local to a function. So then they will always be put on top of the stack. Then you could set in pointers to the task parameters. You set the priority, and you will also have a handle that you can use to refer to the different tasks. And it's also returning some predefined type here that will encode if this was a success or it was a failure to create this. And remember, in FreeRTOS you will have the lower number you send in, the lower priority you will have. The higher number, the higher priority. So this is different from operating system to operating system. So for others it might be vice versa. So then priority 0 will be the highest possible priority that you can have. I can also mention before the break that in a real-time operating system there is always one process that is running. So there is something called the idle process, and actually the idle process will have priority 0. So no other process should have that. So if nothing else would like to execute, then the real-time operating system will throw in the idle process. And then in the idle process you would like to basically save energy if possible. So do as little as possible. So I think we take a 15-minute break, and then we go more in details here. Let's continue. So I got a couple of questions about the code in the break here. I will try to clarify. First of all, it was a question about this task handle. So, and this task handle is a data structure that will contain all the information about every task. So remember when we talked about the context switch. In the context switch you needed to save the program counter, you needed to save the values of the different registers. So all that information is stored in these variables. So for every task you will store the current program counter and the current values of the other registers in this variable. So when a process is preempted, so it will read all the values of the registers and the program counter, store those in this. If ink was currently executing, it will put them into that data structure. And of course this task handle is in the main memory. And then the scheduler will then look at the task handle for the next process to execute. Will read the program counter there, put in the register for the program counter, and all the other variables that should be put in or update the register variables. Remember, the registers were used because all the instructions, for example, if you add two numbers, you need to copy them from the main memory to the register, and the processor can only do computations on numbers that are in the registers. And typically you have relatively few registers, so maybe 32 registers or something like that. So, but while the main memory is very large. So to add two numbers, you put number 1 from the main memory into one register, take the second number, put into some other register, then you execute the add instruction, and you get the result in the third register, and then you need to put it back into the main memory. So that's why all the information in these registers are part of the state. So it's a state that you need to save in these data structures here. So, and that's why you need one such data structure for each task that you have. Okay, that was one question. And then I also got questions regarding the priority. So once again, they don't have to be unique. They can be the same. And if they are the same, then it's basically the policy of the operating system what to do, but most operating systems then does try to be fair among all the different threads with the same priority. So it will let each thread execute for some time, then it will preempt it and let the other thread with the same priority execute. So it will switch between all threads of the same priority. Yep. Okay, I will put this code on the web as well, so you can take a look at it. And we will, next lecture, we will start to do changes to this, and we will see how we can synchronize the different threads here. But this was basically the documentation for the task create function. Yeah, sorry. One more thing. So we created 3 different tasks, but they didn't start to execute until we started the scheduler. Right? So they will just, here we have just initialized all the data structures, and then when we start the scheduler, the system will actually go live, so to speak. Yes. Okay, so we'll look at some examples here. So in this case, we have, so this is the a task function, so we assume that this has been started, created. We have some xcreate task that will specify this task function, and then if we look at what's going on inside here, we will have a variable called PC task name, which is a string, and we'll have some other variable that is an unsigned long. So long here is a integer that has more bits than the normal integers, so typically it's twice the size. So it's usually 64 bits these days. And then we see here we have a for loop, and then we see we have no counter, so we just remember a for loop, they had 3 parts here. So we initialized some counter, and then we had some condition here, and then we had some termination condition here. Oh, sorry. Sorry, this was the termination condition, and here we increased the variable that did the counting. So if you just write like this, then it means that, okay, this will go on forever. So the first thing we do here is that we print out a string, and in this case we print out the task name. So notice also that we have a special function here to do the printing. We have talked about printf before, but when you have multiple threads and so on, you have to be a little bit careful with printing strings, because you might have a context switch while you're printing a string. So in FreeRTOS they have their own function for printing strings, so it's called dprint string, like that. Okay, and then here it just does something, so it will and then it will initialize this unsigned long variable to 0, and then it will increase the value this number of times. And of course what will happen here is that this will just be a delay, right? And then so delay will be the number of clock cycles it will take to execute this number of times. So this is a busy while loop, basically. We just keep the processor busy without doing anything useful. So it's not really how you should do it. As we talked about, if you would like to have a delay, you should ask the operating system to wake you up instead after some time. But at least you can do it, and then since this is in a for loop, it will go back and it will print the task name again. Right? So it will just keep on going forever, like that. And once again, these are put on the stack for each individual thread. Actually, so if we go back to this example again, where we created 3 different tasks, I specified 3 different functions, but I could have specified the same function 3 times. So I could have set this function, increase count to task. We can put it here and here. So what I then would get is that it will create 3 different threads starting to execute here. And since they have, each thread will have its own stack. So this variable I is on the stack, but I will have then 3 different instances of I on 3 different stacks. Right? So it doesn't, so this is just code for the system. So we have to keep that in mind when we think about what's going on here, and understand that these variables are on the stack for each individual thread. Okay, so then we have some other task here. So basically, very similar. It has a different task name. Otherwise, it's doing the same thing. And then we can, in the main function here, we create task number 1, we create task number 2, exactly as what we saw before. And then we start the scheduler. Yeah, and basically now we have started these 2 tasks. So and each task will go on forever, right? So we should never reach this point. So I also got a question about this. So if you actually go here, then you probably, if you reach this point, then your task has terminated, or there was some problem when you did start up when you created the different tasks. Yeah, so what will happen here, we can just see here. So they had, in this case, they also had the same priority, so priority 1, both of them. And since they are always ready to execute, right? They always have a next instruction to run. So then it will pick one of them. And I think you don't want to count on that task number 1 will always start. So you have to be prepared that task number 2 is the first process to execute as well. So if you would like to have a specific order between them to execute, then you have to enforce that with different synchronization primitives that we will talk about next lecture. Okay, so task number 1 starts to execute, and then after some time, since they have the same priority, this will be preempted and task number 2 will start to execute. And then it will execute for the same amount of time, or clock cycles, and then we'll go to task number 1, and so forth. So it will continue like that. So what will happen now if we, for example, gave task number 1, if it had a higher priority? What would change here?
It will continue on with that.
Sorry? Okay.
It will start with task number 1. When the task number 1 finishes, then it lets task number 2 to control the processor.
Yeah, and in this case, task number 1 will never finish, right?
Yeah, because infinity.
Yeah.
Task number 2 will never be done.
Yeah, so they will run infinitely, and then it will always, since the scheduler in a real-time operating system will always only look at the priority. So if there is a process that with higher priority that is ready to execute, then it will be the one that is also executing. So if I gave higher priority to task number 1, okay, then task number 1 will use up all the processing time of the processor, right? So it's not a fair system then. So it's strictly based on priority. So this might or might not be what you want, but be aware of this is how it works. And the reason is of course when you have systems that are time critical, then you as the engineer has to specify what should happen in each situation. So then you do that by working with these priorities. And then you have some other semaphores that we talked about that can be used to fine-tune the behavior, or synchronize the behavior between different threads. As I said, in this case we had the same function. The two tasks, they were basically doing the same thing. They had just had different names. So we could think about now that we just have one implementation of this function, and then we send in the task name as a parameter to the function. So because we have the possibility here to send in parameters. So let's say we now get a pointer to a string, a character array. So what we then need to do is that we need to know that we get a pointer to a character array. So we do that and we let the system know that this is a string that we have got. So we cast it into a character pointer. And then this is the task name. And now, instead of printing out the string itself, as we did before, we print out this variable that was sent in to So then we don't need to duplicate the task function, and we can then use the parameters to differentiate between two instances. So if we look at the main program in this case, so we create then two global variables, one for task 1, another one for task 2, and then we see that when we create the two tasks, we have the vTask function, which we saw on the previous page, and then for the first task we send in this string, and for the second task when we create it, we send in the other string. Okay, so why is this an advantage? I mean, from an execution point of view, they will have exactly the same behavior. But now we only need to represent the instructions for the task once instead of twice as we did it before. So we will save some memory by doing it in this way.
It's very readable as well. Easier to read.
Yeah, it's easy to read and easier to maintain and all that, of course. So, yeah. So we talked about that with the priorities. When you have more tasks with equal priority, then the scheduler will cycle through each one. And there is something to know about when it comes to real-time operating system, and that is that so everything is divided into clock cycles, and then a tick is a predefined number of clock cycles. So that's something you can specify. So, but basically in this case, what will happen here is that the kernel will use a timer, so it will let the time, or it will, in this case, it will start to execute task number 1, and then it will say to some hardware circuit, okay, execute some specific part of the kernel when X clock cycles have elapsed. So this tick clock cycles have elapsed, or has elapsed. And then what it will do is it will switch over to the code in the real-time operating system that will look at the ready queue to see if there is some other process with the same priority, and in this case, assuming that we had another task with the same priority, there was. So then it will do a context switch, throwing out task number 1, throwing in task number 2. So the tick is then this amount of clock cycles that a task is guaranteed to execute before it might be interrupted by the kernel.
Question.
Yes?
Let's say that task 2 had a lower priority than task 1.
Yeah?
It'd still do this intermediate check and jump back to task 1.
Yes, I believe so. So after every tick, the operating system will starts to execute. And in that case, it will just see, okay, there was no other process with higher priorities. It will just keep on going. Something I had in mind. Forgot about it. As you said, if there is a task at a higher priority, it will always be selected. And we already discussed this, but so if you would like to create two tasks of different priority, then you just change the numbers here and you start. So in this case, you have task number 2 will have higher priority than task number 1. So what will happen here is that you get something like this. So task number 2 starts, and then basically what you asked there will be the tick, and it will see that nothing has changed. It will continue with task number 2, and then. Yeah. Is there something else to say about that? Yeah, starvation, of course. So this, now you can say that since task number 1 is starving, when it would like to execute, but it never gets a chance, right? So maybe you did something important, but not as important as task number 2 because it had higher priority, but still, if you had a task that is ready to execute, then typically you wanted it to execute at least for some time in the future. So if you have write programs like this, then you usually have a bug in your program, and it's something you would like to know and to deal with.
Why would you write an infinite program with a higher priority? It should end at some point. If it's higher priority.
Yeah. I mean, if you did it like this, it would be a serious mistake. But there could be other situations that are not as obvious as here, where you have this problem with starvation. Yeah, we will come back to those situations, but it's not always obvious. And one reason is, of course, because one idea behind having these threads is that you would like to have a separator of concerns among the threads. So you think about one subproblem when you write one thread, and you think about some other subproblem when you write another thread. And basically, when you're implementing one thread, you don't know what are the other threads that will be executed at the same time, and what their priorities will be.
Maybe multiple programmers can also be the problem.
Of course, it doesn't help to have multiple programmers. Yeah, so I think we did discuss this. I think we can go to the state machine here. So this is the state machine as the states are defined in FreeRTOS. And basically, when you're blocked here, so there are two primary reasons why you're blocked. Either it is because you're waiting for some temporal event, some timer to expire, or it is that you are doing a lot of computations on data, and the data is provided by some other thread, right? So now you're waiting for that data to become available. So for the other thread to produce the data, this is something where you can use these semaphores that we will talk about soon as well. So once again, you can have multiple threads in the ready state, multiple threads can be in the blocked state, multiple threads can be in the suspended state, but only one thread can be in the running state if we have a single processor. And it's the task of the scheduler to decide which thread to put in the running state. And now we talked about, or we have talked about control tasks, for example. And typically we would like control tasks to execute periodically. And we mentioned that if we would like to wait some time, we could do what we saw before. You go into some for loop, and then you try to by doing that, you could try to time how many times do we need to increase the counter for the process to wait X milliseconds. But that's not how you would like to do it. Instead, you would like to tell the operating system, okay, now I would like to do to sleep for some time. And then to do that, you call a function called vTaskDelay. And then you specify the number of ticks that you wanted to sleep. So now, if you have called this function, the real-time operating system will now change the state from running to blocked. And then it will change the state again when this number of ticks has elapsed. And then it will put you back into the ready queue again. Yeah, let's see, there is an example here. So you have the function, and then you, in this case, you would like to execute with a period of 250 milliseconds. So you, in this case, if you put in the total argument here was the number of ticks, but if you put in the milliseconds here, and then you divide by this number, that is a relation between the number of ticks and milliseconds. So then it will wait for the right amount of time. One thing to note, though, is that this will execute for exactly, or it will wait 250 milliseconds in this case, right? But let's say we would like to execute periodically, and we did something that was rather computational intensive here. So let's say we did something for that took 100 milliseconds to execute. So that means that if we, in this case, waited here for 250 milliseconds, then we would execute periodically every 350 milliseconds. So then there is something called vTaskDelay until that will deal with that. So I have an example on that as well on a later slide. But it's important to know that the vTaskDelay will just wait for that amount of time. So it doesn't automatically guarantee that it will execute periodically with this period. Yeah. So in this case, you see here, so we have two tasks. Task 2 has the higher priority in this case. So they starts to so task 2 has the highest priority to run first. It prints out the string and then calls the vTaskDelay. So it will block, and then it can, since it's blocked, it's no longer in the ready queue. So now the scheduler can let task number 1 execute, right? Because now that's the process with the highest priority. Then it will do its work, and in this case it will also try to, or it would like to sleep for some time, so it will execute another delay function, and then now we have 2 threads that are both blocked. So we have no thread in the idle or in the ready queue, basically. But as I mentioned, there is always one thread in the idle queue, and that's called the idle process or idle thread. So it's the lowest, is the thread with priority 0. So if nothing else can be executed, the scheduler will start to execute this. And here you try to save energy and resources when you do this. So now nothing will happen until this time in the future where the number of clock cycles has elapsed. That was specified by this vTaskDelay. So now task 2 has been changed state from blocked to running. and now it will have higher priority than the idle task, so task number 2 will start to execute again. Okay, and in this case it will execute the task delay function again, and then task 1 becomes ready and can execute. So it will continue on like this. This is the idle task we talked about. So it's automatically, this is not something you have to create, it's always done. And basically it ensures that something always runs, and it has priority 0. Yeah. So we saw here that using this, calling this task delay is much more resource friendly than using polling, for example, than just increasing some variable. Or if we would like to for example, we have some piece of code that should be executed once some variable has changed state. So then it's better, for example, some value from the AD converter. So then it's better to let the hardware tell me when the variable has changed state, and then we will execute some code instead of just keep on checking the value of the variable all the time. So this is so implementing embedded systems is about knowing how to use these different concepts that the real-time operating system will provide to us to do this in a nice way. Okay, so we have another example here where we have a continuous process that will always do something. So it will just, in this case, it will just print out the task name in an infinite loop, like this. And then you can have another task that will print out its name, and then it will call in this case the vtask delay until, and this is the function I was just talking about. Because if we look here, so this is a variable for this task, and we initialize it by getting the current number of ticks from the real-time operating system. So this is the number of ticks that has elapsed since the system was started. And in this case, so we send in the address to this variable, and then as a second argument we specify basically the period here. So the milliseconds divided by, so it will convert this into the number of ticks in the same way as before. So if this, so let's say this one, the first time we executed, this one was 1,000 ticks, and then we would like to execute every 100 ticks. So what will happen here is that we wait until 1100, and then the next time this wake up time will be increased by this number of ticks. So then it will wake us up at 1200, at 1300, and 1400, and so forth. So by using this, we will be guaranteed to execute with the given period. Right? So it doesn't really matter as long as it will take less than, in this case, 100 ticks to execute the code here. Then it will run. So, but there is one thing to keep in mind though, now as well, and that is that there might be other processes that are also running, right? So this will put us, it will guarantee that we sleep until the start of the next period, but it doesn't mean, and basically the what will happen then is that we are put in the ready queue, right? So then it's a different decision among all the processes in the ready queue which one to execute. So it might be that although this task is ready to execute, that there are some other tasks with higher priority. So what we actually get here is that we are guaranteed to be put in the ready queue at 1100, 1200, 1300, 1400, and so on. But it doesn't necessarily mean that we start to execute at 1100 sharp. It can be 1120 or something like that. Yeah. So when we implementing control task, we should use this vtask delay until, because it's definitely better than the vtask delay, because we are not sensitive to how long it will take to execute the other instructions here. Okay, so let's see with this example. So we had a continuous task that we had two continuous tasks that always wanted to execute, and they had the same priority. So the scheduler will do round robin. It will divide the time between them fairly. So it will execute the tick amount of clock cycles, and then it will switch to the other task, execute that a certain number of clock cycles, and go back and forth. And in this case, we had a third task that was periodic. So it was blocked until some timer occurred, and then it did its work, and then it will, when it was done, it will go into the blocked state again, and then the system will continue to execute the other two tasks that are always ready to execute. So it's clear. So you can mix between periodically executing tasks and tasks that are always ready to execute. Yes.
So if one periodic task is not able to actually reach that point because there's some other task with a higher priority, then using until as a block state will do I see it correctly that will then execute more quickly the next couple of times to make up for that time, and the other one will not?
Yeah, it's a good question. I might be wrong about this, but if I understood the system correctly, what will happen is that you will actually, so let's say you executed at 1,000 ticks, and then there was some other task with higher priority that was executing for 200 ticks, and this one wanted to execute at 1100, for example. So what it will try, so it will, every time this is executing, so it will be increased by this number of ticks, so 100. So I might need to look this up, because, but it, from my understanding, it was that it will execute the right number of times, but it can be delayed. So it will be increased by 100 ticks every time. But I have to really check the documentation to know what it's doing in this case. So it might, so different real-time systems might have different ways to deal with this as well. So this is normally a situation you would like to avoid, of course. But it might happen, so it's good to know what happens. Other things that you can have tasks that will create other tasks, for example. So you don't need to know beforehand how many tasks you have. So it's something that can change during the execution, for example. And you can also change the priority. So in FreeRTOS, they have functions to change the priority of a function dynamically while it's executing. You can also ask for the priority. Again, you can delete other tasks and suspend them, and so forth. Although it's good to know that when you're implementing control systems, so since they are quite often critical for the correct behavior, so it is a good advice to try to allocate things statically. So to have statically allocated memory, so you don't use too much dynamic memory, because then you can run into memory problems, as we said, or that and that you're also careful with having processes started dynamically and ending dynamically. Because if you do a lot of things dynamically, you can run into problems like, for example, that you run out of memory. And if you have a safety critical system, you run out of memory, that's not good. So, for example, if you go back to a PLC, programmable logic controller, that I know that some of you worked with in your bachelor's, for example, there you typically only have statically allocated memory. Oh. Yeah. So with that, I think we end. And then we continue to look into these race conditions and synchronization primitives on the next lecture on Thursday. And now there is consulting hours, if you like. You can go, and remember, if all of those that didn't finish everything for the last week, so yeah, the session you had last week, so continue to work on that this week as well.